Hello, everyone. Welcome to my presentation. I'm Tongwei, third-year PhD student, a member of Cake Lab in WPI. Today, I'm going to talk about our paper, Breaking IoT Software Homogeneity with Protocol Mutations. This paper is advised by Professor Lorenzo Di Carli, co-worked with Ryan Williams, Shandu Ganguly, and Professor Long Lu from Northeastern University. In this talk, we will introduce a moving target defense technique, which alters the syntax of network protocols. It introduces protocol mutations at the compile time, so as to protect self-contained IoT deployments like military, industrial, or smart cities. IoT software homogeneity is a phenomenon that oftentimes different devices reuse the same open source components and or are built on the underlying platforms provided by the same manufacturer. From some perspectives, it has advantages like convenience, but large numbers of network-connected devices with homogeneous software stack but poor software quality result in significant replication of the same vulnerability. Researchers and existing reports have shown that a single widespread vulnerability in a highly popular device can enable large-scale attacks and cause significant loss. For example, a single zero-day affecting Huawei home gateway devices enabled cybercriminals to create a 100,000 strong botnet in December 2017. Our paper targets a style of IoT and embedded systems that we term self-contained critical deployments. We define SCDs as deployments, where the set of devices that belong to the deployment is a priori known, and an attacker can communicate to the deployment to cause disruption or even human cost. The reason why we target SADs is they are self-contained with a single organization, which enables us to change protocol stack without concerning compatibility. More specifically, targets of our paper can be IoT machine-to-machine protocols and other message-oriented protocols like MQTT or lightweight machine-to-machine protocols, which are used widely in practice. Best practice security measures, such as robust authentication, can help mitigate this risk. But the real experiences demonstrate that they can be bypassed because of vulnerable implementations. Thus, we propose the use of software diversity as an approach that can provide additional security when paired with best practices. The key idea is to mutate the protocol to generate functionally equivalent, yet syntactically or semantically different implementations of protocols. Introducing variations can prevent an attacker from devising a general exploit by analyzing one copy. More specific, network protocol vulnerabilities are nearly exclusively triggered via network input. Thus, it is reasonable to focus on deploying diversity within application components that deal with network communications. A CV reported the Eclipse Mosquito broker up to version 1.4.15 doesn't reject strings that are not valid UTF-8. The bug will disconnect other clients when they receive those invalid messages. By designing a malicious message, the attacker can attack every Eclipse broker with this version and cause vast disconnection. One solution is we can mutate the protocol to generate functionally equivalent yet syntactically or semantically different implementations of protocols. For example, we mutate the flags field in the packet generated by the weak version Mosquito, change it from 36 to a new value 70. And to be clear, this mutate will only change the syntactic format of messages. Both the client and the server will handle such changes accordingly to ensure the consistency and the correctness of this field's functionality. So by doing this, the original software has been changed. So does attack surface. The attacker will not be able to simply launch a simple same attack on different brokers. In our threat mode, there are two types of attackers, both armed with a standardized exploit and aiming at commandeering devices. The first type is the off-path attacker, who can send traffic towards potential victims and receive replies, but cannot observe the victim's communication with other nodes. The second type is the on-path attacker, who can send and receive traffic to or from victims, and observe communications between non-compromised devices prior to the attack. The attacker may use its on-path capability to reverse engineer wireless communications and identify vulnerabilities, so as to inject messages and better compromise devices. In this paper, we only focus on off-path attacker and leave on-path attackers as future work. To deploy diversity within network communication protocol applications, there are some challenges. First challenge is how to identify both code used to construct messages and parse them. It's important that changes must be correctly written into the outgoing packets and reversed from the incoming packets. The second challenge is how to keep any modifications symmetric. In other words, we need to make sure changes in how protocol messages are generated must be reflected by changes in how the same messages are parsed. The third challenge is how to deal with reverse engineering. We can split mutations to two types, static and dynamic mutation. A static mutation is one which is statically embedded into the protocol firmware at compile time and always exhibit the same mutation. Static mutation can be reverse engineered by on-path attackers who can observe traffic. By analyzing traffic, attackers can know how to mutate an original message. And a dynamic mutation is one which can be enabled or disabled without recompiling the program by acting on appropriate control parameters. Thus, dynamic mutation is necessary to prevent inverse engineering. To solve these challenges, we propose an approach for analyzing and mutating network protocols in the IoT space. It can automatically diversify and specialize network protocol implementations. With our approach, we are not aiming to remove vulnerabilities from a code base. We are changing the control or data flow used to exploit some vulnerabilities. This is an overview of our approach. It consists of two systems, PACO and Aloja. PACO's full name is Parser Constructor Extractor, and Aloja is a mythical creature from Catalan mythology. It's able to shapeshift or mutate into a bird. At the beginning, PACO will analyze input program to extract useful information and output them to the next part, Aloja. And Aloja will do an advanced analysis and finish the mutation injection and mutants testing. Let's look at the PACO first. So what's PACO? PACO is a static analysis tool. It's a code understanding tool to locate network-related software components. It can extract necessary information for Aloja. The necessary information means those information that Aloja needs to finish the advanced analysis and mutation injection. PACO consists of three steps. First step, find network-related structs. Network-related structs refers to structs that are used to build or parse message packets. PACO first gets all structs from the application and remove non-network related structs based on the struct set, which includes standard library-defined structs like address information. Then it backward traces the arguments of socket read, write, send, receive, and or memory copy function calls to find structs used to store outgoing messages and incoming messages. Second step, PACO analyzes each function in the application to find all functions that are used to write or read network-related structs PACO found in the previous step. We consider these functions as network-related functions. The third step, Protocol builds a graph to display relations between found functions and structs in the previous steps. Now we get to the second part of our whole approach, Aloja. Aloja is a static analysis and mutation injection tool that can further analyze information from Protocol outputs, inject mutations based on this information, then test and output useful mutants. Aloja consists of 3 steps. The first step consists of 2 small actions. Aloja first filters out unsported fields and corresponding parser and constructor functions. Then it refines the parser and constructor function sets based on the function level code graph. Sported struct fields refer to any fields fitting following rules. Rule 1. The sported field should have a data type that is sported by Aloja. Rule 2. The sported field should have both parser functions and constructor functions. To refine parser and constructor function sets based on the function level code graph, the key idea is to remove parser and constructor functions that are unlikely to directly affect protocol messages. More specifically, as shown in the example figure, Aloja will remove each parser which has a direct edge from another parser, and each constructor which has a direct edge to another constructor. In the second step, for each sported field and the corresponding parser and constructor functions, Aloja will generate all possible tuples. Each tuple consists of 1 field, 1 parser function, and 1 constructor function. Then for each protocol, Aloja chooses the mutation schemes and inject the code template into the original IR file, then output the mutant, which is a mutated IR file. In the Aloja, we currently have 3 mutation schemes: refactor global variable value, mutate field value, and encrypt field value. The last step of Aloja is correctness check. This check is to make sure each mutant Aloja outputs to the user is correct and useful mutant. There are also 2 rules for a correct and useful mutant. Rule 1, the mutant should keep functional integrity. This rule is to make sure the mutant can correctly work. Rule 2, the server mutant should block the message from unmutated clients. This rule is to make sure our mutant truly changes the messages and affects the communication. So how to do the check? Aloja first runs a mutated server and client to check whether they can communicate correctly. Then it runs a mutated server and an unmutated client to ensure that the communication fails. To evaluate our approach, we run it on 4 different IoT implementations. The results of Protocol in identifying network-related structs are shown in the below table. False negatives come from network-related structs not being directly used for memory copy or memory operation or network operations. False positives occur due to Protocol heuristics being misled by the presence of system calls that are frequently but not always network-related. Overall, Protocol gets a higher accuracy, larger than 97%. The results of Protocol in identifying network-related functions are shown in the below table. Overall, Protocol achieves larger than 93% accuracy. Analysis of mistakes indicates that they occur due to mislabeling of the corresponding structs. To evaluate the mutation, we first did correctness evaluation. We run unit tests against the mutated version of each protocol. The results are shown in the below table. There are some failed tests. We manually go through each of them and ruled out these failed tests as benign, as they are our expected behaviors. Our mutation strategy is specifically designed to trigger failures like this. Besides, we also run fuzzing tests against the mutated version of Mosquito. The fuzzer ran for around 1 hour without triggering any unexpected behavior. We then did exploit mitigation evaluation to evaluate mutations. We reliably reproduced 4 CVAs, 3 for mosquito and 1 for wakama. All CVAs are constructor or parser related, fit the focusing area of our approach. As shown in the below table, all these security bugs can be triggered by sending a designed malicious message. We tested the reported vulnerabilities before and after running our systems on the vulnerable version of applications. The results show that our approach can successfully mitigate all exploits we show in the previous slides by modifying the input necessary for triggering vulnerable code. And to be clear, our approach mutates the control flow necessary to reach the vulnerable sink instead of removing a vulnerable code. We also evaluated the impact of code graph-based filtering heuristics Aloja used to refine parser and constructor function sets. In total, Aloja generates 422 fewer mutants, which is around 25% of all mutants. Only 6 of them are useful mutants, which is around 33% of all useful mutants. We conclude that the filtering heuristic selects and removes incorrect mutations with reasonable accuracy. To evaluate the performance impact of our approach, we examined 2 aspects. First, the compile time overhead of running our systems. It's measured by timing the overall compilation without and with our technique, including Paco and Aloja. Second, the runtime overhead due to the additional computation performed by injected mutation templates. It's measured by sending 10 messages per client to the server via the respective protocol with 10, 100, 500 clients in the network. Each message is 10 kilobytes. The results are shown here. The upper table shows the incur compile time overhead for our approach and C-long. Most of increased overhead is due to the testing mutations in Aloja. For each possible mutation, Aloja must run the mutated application twice. The significant compilation time for C-long DDS indeed results from the fact that its large code bases induces many candidate mutants. Thus, then be voted on average tested a mutant requires 10 seconds. The process could be sped up by better mutation filtering heuristic, which we leave as future work. The lower table shows the overhead, a message send latency introduced by mutations. Results show that overhead is generally limited. Furthermore, the relative overhead generally increases sublinearly with the number of clients, and notably decreases in the case of Wakama when going from 100 to 500 clients. This fact in particular led us to suspect that 100 client Wakama results may be affected by an experimental artifact, but were not be able to trace the source of the deviation. In conclusion, we propose a technique for injecting mutations into implementations of embedded or IoT-oriented network protocols as a form of moving target defense. Our evaluation shows that our approach can correctly identify message-related code and inject mutations, which effectively prevents current exploits without breaking the protocol and only introduce limited overhead. Overall, we provide an important foundation for moving target defense based on protocol mutations, including the techniques and the libraries that can help more researchers and developers. That's all about my sharing today. Thanks for listening. Any questions or advices?